A box of mass 0.20 kilograms is released from rest at the top of a frictionless curved section of track that is 1/4 of a circle. And where is that on the picture? That's right over here. It has a radius of 1.5 meters. When the box reaches the bottom of the curved track, it slides on a rough horizontal section. And whenever you hear the rough, think friction. The coefficient of kinetic friction between the box and that section is 0.20. Find the velocity of the box at the bottom of the curved section of track, right there. It's going to be A. Find the stopping distance of the box on the horizontal section of track, so that will be this distance here. And then, if friction is present on the curved section of the track, how would it change the answer to part B? First, find the velocity. So what we're going to have is at the top, we just have potential energy, and at the bottom, we just have kinetic energy. So really, the only trick is to find this height here. But since we're given the radius is big R, and just to help you visualize this, we'll kind of draw the circle out. That's not too bad. You can also see that the height of that mass is also big R. So here we go. We have mg times r is 1/2 mv squared. The masses cancel. We get velocity is the square root of 2gr. We plug in our numbers, and we get a velocity of 5.42 meters per second. Notice we're going to keep an extra significant figure, because this is an intermediate solution, and we're going to need the velocity for the next part. So even on the AP exam, if you were to put either 5.4 or 5.42 meters per second, that would be just fine. Find the stopping distance of the box on the horizontal section of track. Well, the first thing you need to do is find the acceleration. And to do that, you need, a free body diagram. This is pretty straightforward. The only force you have acting on this piece is the friction force, and it's opposing the motion, so we have it going to the left. Then you have the normal in mg. So we have minus F sub k equals ma. We substitute in the value for friction, which is mu times the normal, which is mu k times mg. M's cancel, and we get an acceleration of negative 1.96 meters per second squared. Again, an intermediate solution, so we'll keep an extra sig fig. And now to the kinematics part of this solution. So this is kind of cool. In just a few slides, we use conservation of mechanical energy, then dynamics, and now kinematics. We're not interested in time, we're interested in distance, and we're given an acceleration and an initial velocity. So that's just the third kinematics equation. And we're trying to find delta x. Now what's going to be our final velocity when we stop? Well, that'll be 0. So we come up with delta x is minus v0x squared over 2a. We solved for v0x earlier. That was conservation of energy. We solve for the acceleration using dynamics, and notice the extra sig figs there. We get delta x is 7.49 meters, and then again we wind up with just 2 sig figures, which is 7.5 meters. Don't worry too much about this on the AP exam, but if you're off 1 or 2 significant figures, it does not matter. If friction is present on the curved section of the track, and that's over here, how would it change the answer to part B? You now have an external force, friction, that will do negative work on the box as it traverses the loop, so the work-energy equation would be used in place of the conservation of TME to find the kinetic energy, to find the velocity. So we have our initial potential energy plus the work is going to be your kinetic energy. So that'll be potential energy minus, because it's negative work, friction opposes motion, the friction force times the distance over which it acts. And this is just 1/4 of the circle, so that would be pi over 2 times r. Therefore, your kinetic energy at the bottom of the loop would be less than in part B, so the velocity would be less, and therefore the stopping distance would also be less.